This is going to be your lab today. So it's the 6-4 alternate lab with the conservation of momentum. So remember that the conservation of momentum is when all of your forces are internal to your system. So the momentum that you start with is going to be the momentum that you end with. And with that idea, we're going to talk more about elastic and inelastic collisions and view them on this virtual setting. So the first part is to go to the Collisions Lab HTML5. So if you go ahead and click on that link, it's going to bring up this Collisions Lab PhET simulator. And what you need to do is go to the introduction screen. So this is going to open up this little handy dandy tool. And what I want you to do is click on more data. By allowing more data, you can not only see the mass and position, but you can also change the velocity that these balls or that these objects are starting with. All right, so you have this option to choose the mass. Again, you can type it in right here. And you can also have a velocity, and this can be positive or negative, but it can only go up to 3 and positive 3. But let's go through this lab and see what we need to do. So again, the objective is to understand more about momentum, where P is equal to mv, and understand elastic and inelastic collisions. So elastic collisions, so you start with an initial mass and velocity before, plus the initial mass and velocity after, and you're going to end with a mass and velocity total here. Okay, so you're again, it's going to be a little bit different from what we have shown in class, but basically it's following the exact same format. So this mass and velocity 1 before the collision, and this mass and velocity before the collision again, and that's going to be equal to the mass and velocity after the collision for mass 1 and the mass and velocity after the collision. Again, this is for mass 2. So when things collide, it's for two objects, but it still follows the same principle as the conservation of momentum. So if this equation looks weird to you, go ahead and write it how I have shown it to you. But this is kind of an easier, more confined equation here so that we don't have to keep writing the same thing over and over and over again. So I ask you, what is an elastic collision? So what two things are happening there, or what two things aren't happening? That's what I want you to describe. And if you don't know where to find that information, go back through your notes. And for this next section, working with this table, we are to simulate the 4 elastic collisions below, completing the table using math formulas and the simulation. So for trial A, we are to set the mass 1 to 2 kilograms, mass 2 to kilograms, velocity 1 to 1.5 meters per second. And we aren't given the velocity 2, but we know that the total momentum of our system needs to be equal to 0. So what velocity here is going to give us a total momentum of our system equal to 0. This is when you have to use math. All right, so if this is going to be positive, then how do we get this equal to 0? Hint, hint, nudge, nudge, this has to be a negative number. Okay, so I want you to run through the simulation, finding out what we have to put in here. Again, it has to be negative, and it has to have the total momentum equal to 0. And then I want you to tell me what after the collision, what that looks like, what the velocity 1 and what the velocity 2 are going to look like after the collision. Because this is elastic collisions, these two things aren't going to combine. That's why we're not given a second mass or a first mass, because the masses are staying the same. It's just that the velocities here are being transferred from one another. And I just wanted to point out that on this lab, we are in the elastic setting here. So you can also be in the inelastic setting if you just scroll this thing over, but we want to be 100% elastic. Okay, so again, you just want to plug in the masses that you need, plug in the velocities that you need, whether it's positive or negative, and then the momentum totals are going to be shown to you right on this section here. Okay, I would almost suggest to put this on the slow setting rather than the normal setting. If it helps you to have it on the normal setting, I always find that it's better on the slower setting, honestly. But either way, it's going to show you the exact same data just at a different rate. So I want you to do this for these 4 trials here. Again, you're adjusting the mass for each, and again, the total momentum initially has to equal the total momentum finally. So if we are trying to get 0 momentum for our system, what velocity 1 does this have to be in order for this to be 0? And as you go through, again, just setting these things according to this table and then solving for our final velocity here. And at the end, I ask you to show mathematically the total momentum for a collision in trial number 1. So this is trial number 1. That's the first collision that we're going to do. So basically, I want you to show me mathematically that this is actually equal to 0. How does that work out? So I want you to use the equation that I give you up here, or the one that I gave you that I told you to write down in your notebook. Either one is absolutely fine, but I want you to show me mathematically why this works, why the initial momentum is equal to the final momentum. And then you can jump down to inelastic collisions. So inelastic collisions are when the masses are going to combine here. So in order to get the simulator onto inelastic collisions, again, you're just going to scroll that little tab over. So the elasticity here should be 0%. Okay, so when these things combine, they should deform and create heat. But the same idea and principles apply where we have to adjust the mass accordingly and adjust the velocity accordingly so that we can get the correct momentum that it's telling us to get in the table. For this one, it's pretty simple here. We're given a 2, 2, and a certain amount of velocity here, and we just need to plug those values in and solve or get the after collision velocity. So again, we're not given a mass 1 and mass 2 after the collision just because those things change. Those things are going to combine, and we're going to be left with a after collision velocity. Again, just solving it out the same way where the P total has to be equal on both sides. So I just kind of threw this in here to kind of give you a little bit of a challenge, but again, you're just solving it the exact same way that you would solve for the momentum for 1, solve for the momentum of 2, and make sure that the total momentum or that net momentum initially is equal to that number, 10 kilogram meters per second. And then once you are done filling out this table, I want you to again show me mathematically the total momentum before the collision in trial 1 is conserved after the collision. So again, showing me mathematically this trial right here. So you're using this mass, you're using these velocities, and you're going to use the after as well. And feel free to use this equation right up there. That's the inelastic collision equation. If you have any trouble on it, I mean, you really shouldn't, but just make sure that you re-watch this video where I'm explaining, okay, all you have to do really is plug in the masses that it gives you or solve for the velocity first before, and remembering that the total momentum initially and after has to be equal. All right, so make sure that you're really reading through these directions, going back through your notes, and remembering that collisions come from the conservation of momentum. So all of the forces are internal to your system. So whatever you start out with momentum, you need to end with momentum. All right, again, the products is what matters, not the actual values. All right, so try your best on this. Try to get it done today. If you do not finish it, make sure that you finish it for shop week homework, but recognize that you still have that egg drop project to do. So don't try to stress yourself out. Try to get this stuff done as soon as possible. All right, I will see you all soon. Bye, y'all.